So this is the last lecture of the course, and some people actually did send in some pictures of their pets. I don't remember all the pets' names. I do know that is Bailey the dog, who looks like some Labradors I've had in the past, and probably like all Labradors, is a wonderful dog and is rather destructive about his or her toys. I've known both male and female Baileys, and lots of really good cat photos. What's really cool is the predictive text on PowerPoint knows that this picture here is of a cat wearing a hat. And it says this is a picture of a cat wearing a hat, which is awesome. This is not as awesome. So I think we want. There's a lot of interest in talking about polymerization reactions, and I think we just did this example. I'm going to do a slightly different version of this example. Oh shoot. Okay. We're going to switch from a polymerization to a not polymerization. And we know it's not a polymerization. This one's not a polymer because I think there was a polymerization we did last class. Basically the same example. We know it's not a polymerization. Yeah, AIBN is still there. We know it's not a polymerization because we have a second thing in here that we can react with. So, no surprise to anyone who's probably watching this. The pre-initiation is AIBN does its decomposition. We have that mechanism drawn out a handful of times, so I'm not going to do it again. I'm going to just do the short form and just get us to where we're going to go. If you're doing an exam, you can't do the short form, you need to draw it all out. Yeah, so I'm changing it a little bit because I'm not doing the polymerization this time, Anita. We did the chlorination of this last class. We did the chlorination, but not the polymerization. Okay, then we're doing the polymerization. Okay, polymerization. Now I'm going to be careful about asking this again because it does get a little messy. It does polymerize, but it gets a little bit messy. So again, AIBN, heat, radicals. Sweet. Okay. Then this radical is the easiest one to form. So that's what we're going to do. And that radical is in resonance, so it's very, very stabilized and all that. But we want the most stable double bond we can get, and in the product, and that's that. So we're going to actually leave the radical like that. That's the reactive radical. This, of course, is the initiation, because we are making a radical that's going to take part in a reaction. If there is a hydrogen adjacent to the double bond, that will almost always react first. We're going to show those in polymerization. It gets a little more complicated. But you always make that radical by abstracting a hydrogen next to the double bond, alpha to the double bond. That's always preferred. Because this is both this is not as stable, but it's going to be the reactive conformation. So the radical is more stabilized if we draw the resonance structure. But the product is going to be more stable if we use this. And this is from the resonance structure. These aren't intercovariant, this is equilibrating. We're going to have a more substitute double bond. And so we prefer to have the double bond substitute here in the product than on the terminus. Even though the radical is more stable like this, and that's really important for making sure that this radical can be formed. But once the reaction happens, if you can think of, we are going to make products, these are the same energy because of the same thing. So yeah, we'll come back to this in a second, Mohammed. these are the same thing, but they're going to go to different products. And the product that's more stable, which is this one, is going to derive from this one, is going to have a lower energy transition state because the styrene material is the same thing. And if the product is lower energy, the transition state is going to be a little bit lower in energy. So it's going to be easier to react from this conformation or this resonance form. But this is our initiation. And then our propagation. Well, there's a few things that could happen. So one is if we take that and if we react it with this, and we take the weakest bond available, which is the hydrogen, oh look, nothing happens. That wasn't productive. We get the same thing on the styrene materials and products. So we get something happen. So this is non-productive because it produces no product. What's going to happen need to make sure I draw this. I am confusing myself. There's that. So this is where it can be really useful to label your atoms. So we make this. So this is no, you don't need to include the non-productive ones. Yeah. Deepen, yes. So this is where this gets a bit tricky, and why these make kind of messy polymers when we have these methyl groups, and why I'm not going to ask you a question like this is because now this can propagate and react with another double bond and continue, and that's the most productive thing to happen. And with this particular system, it's actually quite likely. But with other ones, what we're end up going to do is we're going to abstract a proton from another equivalent of this, and we're going to chain terminate a little early. So just going to make some dimers, really. And so that's a little bit of the worry about using these kinds of systems. So we aren't going to see these kinds of systems on the exam because we run into this problem. So you run into a risk when you're trying to polymerize in the presence of an alpha hydrogen. Now, there are some examples, and this is one where this actually is slightly suppressed, and it's not as likely to happen just because of the stability imparted by the cyanide. And so this particular monomer does behave a little weird, and it does react with a double bond and make proper polymers, just like we've seen with other attacks and double bonds. But this can happen if we have an alpha hydrogen. So basically, this comes down to I am not going to ask a question like this. I want to highlight I'm not going to ask a question like this. No, the one place you're not going to put the radical is you're not going to put the radical on A, because that would just be a secondary at radical, and that would not be stabilized. This radical here on B is stabilized by resonance with the cyanide group. There's no way the radical is going on A. It's like the only place you can't put it. You can put it anywhere else. Okay. Yeah. Okay, well, if this goes ahead and does make the polymer properly, so the next step of the propagation. So again, following this rule of let's try and draw these things out like this. We'd have a cyanide on here. We'd have a radical. Then I'd have, now the first monomer is going to look a little weird. But this would react with where R is this whole thing that I'm not worrying too much about. And so now we're starting to see the repeating subunit. So we'd have that for the propagation. Termination here would probably be hydrogen abstraction. And you're not going to get a super long polymer because you are going to have this competition from what I've just shown there. So that's your propagation, then your termination. Well, we've actually drawn a termination step already. This is basically your termination step here, where your growing polymer chain, this radical here, gets quenched by a hydrogen. Yeah, so it's from the less substituted radical because it makes the more substituted double bond product. Like the thing to remember is this isn't like a carbocation where the carbocation you attack the more, you wouldn't worry about where the double bond is, you worry about putting the carbocation in a more stable place because that's where the biggest positive charge is, and that's where you attack. The radical is neutral. So the radical is just, yeah, like it's resonance stabilized. It tells, like, the fact that it's resonance stabilized is the important thing. That makes the whole radical possible to make. But where that radical is much less important than where the double bond is. And we want the more substituted double bond because it's the more stable product. You do not need to include radical with wall for termination. You can if you like, but terminations on the exam for standard, anti-Markovnikov addition or radical chlorination, all you need to include is you'll have two different radicals in your propagation, radical A and B, so you'll need to include A plus A, B plus B, and A plus B. I don't quite know what you mean, Amber. I'm going to move on because there's more stuff I want to cover today. Yes. Radical reactions have a lot less variability than a lot of the other types of reactions we've got. Can we do some questions that are likely to be on the exam? Nice try. So one of the confusing things, and I kind of understand it, but it is a challenge. Is there? Yeah, can we just do the exam? Um, yeah, Alia. Yeah, I'm going to avoid the extra methyl group if I do that. The you could, hater. Well, the concept is similar. So this came up. I'm only answering questions that people pose because I really can't talk about what's going to be on the exam. But there are multiple versions of the exam. We're trying sort of drawing from similar pools. And again, I'm going to be sending out this sheet on what's going to be on there, but there's going to be multiple choice and long answer. Well, mechanistic answer. The multiple choice you'll answer on the Mobius software, and it's click a radio button, and it's relatively straightforward. They're not like the Mobius; they're much simpler multiple choice. Anyways, got a question about this, which is, can we do one where we're talking about number of equivalents of something? So a little bit confused. So in this example here, we have this starting material we're adding 1 equivalent of hydrogen iodide and 1,000 equivalents of ethanol. Yes, you're able to go back on multiple choice. I have no idea what the exam is going to be out of. Somewhere between 100 and 500. Probably closer to 100, but maybe 200. Maybe 160. Yeah. I think what I can do is try and get you to see some more of the multiple choice in one at a time, but it is kind of, I think right now it's one at a time. But you can scroll back and forth. There's kind of actually a navigation menu where you can click through and sort of quickly go to what you want. So what this is telling us is basically we've got some strong acid, and this is just catalytic. There's just a little bit of HI present. So we have a good leaving group. We've got heat. And we can make a nice big tertiary carbocation. I'm looking around. I'm not seeing a really strong nucleophile. I'm not seeing a really strong base. So I'm not thinking that I'm going to be looking at E2 or an SN2. This is looking a lot like an SN1 or an E1. We have a carbocation. Now, there is some I minus present. But for every molecule of I minus, there are 1,000 molecules of ethanol. So what is more likely to interact with this molecule? No, not really. Yeah, ethanol is going to react. So the important thing here is to think about the ratio. It's really easy to go, ooh, I've got iodine, run with the iodine. But you got iodine, but you got 1,000 ethanols. So I would accept two answers for this. I would accept either an E1 or an SN1. Under these circumstances, I am leaning strongly towards the SN1. And now that's for two reasons. One, you have to space stuff out. If I'm asking for a mechanism, you have to provide every mechanism. So Janik asked, when showing mechanisms on the exam, could we do multiple steps at once, or do you want to space everything out like this? If it's asking you for a mechanism, you need to show every intermediate that's formed. So if it's asking for the product, you can sketch however you want to do it. Again, we're talking like I've got Jess's cat up here on one of my monitors. So going back to thinking about, and that's a skinny cat, Jess, just like ethanol. And so we have a skinny cat. Our door is a little tight because this is tertiary, but there's only methyl groups here. There's nothing bigger. So this is about as small a tertiary as you can get. So small. The SN1 is probably favored in this case. But I would accept for full marks a Zaitsev elimination as well. I wouldn't accept a Hoffman elimination because this is not a Hoffman base. I'd probably pick a bigger nucleophile. So instead of Mohammed asked, what will make it lean towards E1? The heat helps lean it towards E1. No, you wouldn't get any marks off. The E1 is just as correct. I think you're going to get a mixture of the two. This one, it's hard to tell which one it is. E1 and SN1 are very, very leaky mechanisms. They leak into each other. It's hard to get one or the other when you're using alcohol stuff. Yes, there's a bonus question on the exam on the final, and we've talked about that in class before. It is neither E nor Z, Amber. It is because these two are the same. So you can't assign E or Z. Yes, absolutely. I'm really sorry. Yes. Yeah, absolutely. Thank you, Deepan. You're absolutely right. Yes, you do need to show. I skipped a step, and I'm really sorry. You do need to show the removal of that extra proton. Okay. Yeah, isopropyl alcohol would definitely be E1. I don't think it would actually lean. I think it would lean. Well, I think there we would shift to like 90% E1, 10% SN1. So there, I would expect you to give me an E1 product. Um, yes, Janik, I think you've summed up in a sentence what I've tried to say. I think I've said that, but it is good to hear somebody else say it. No, you don't get marks off for not showing any lone pairs. You don't need to. Yeah, you would not include E or Z for this compound because there is no E or Z. Um, yeah, so Keith Wong said, if I missed Nina's question, if it was ethoxide, not ethanol, would that favor E2 more than both S and Y and E1? So if we had this with ethoxide, I'm going to argue no reaction because OH minus is a very bad leaving group. Yeah, you could draw an acid base reaction, but then it wouldn't get us anywhere. You'd make an O minus there, but that's a stronger O minus than that, so it would just reprotonate itself from ethanol. So nothing would really happen. It would be unproductive. What's the average on the final? This is not a normal final. I have no idea. I suspect that my average is going to be a lot higher than it normally is. No, I'm not going to have any no reaction answers on the questions on the final. In a normal year, I might think about it, but not this year. We're all, we've had enough. We've all had enough. Like, it still tests the material. Um, for full mech questions, we have to include EZ. Only if it's relevant and I ask you to name the compound. Otherwise, you have to get the right compound, but that's it. There's not much else to do. Okay, so what I want to do is I want to skip to the next one. Back. It's got a lot to cover because you people are voracious in your attitude. So I've posted a video of this. I know that for some people, the video they still ask me to do it again. So in the interests of by popular demand, I guess I'm doing this again because I got multiple people asking me for this. Time is it? Okay, we're good on time. Okay, double bond. Ozone does help if you draw ozone right. So if we think about ozone, we kind of have a nucleophile, electrophile in the same molecule. So it acts as a nucleophile and it acts as an electrophile. If you're really good at ozone, you can tune out for the next 3 or 4 minutes. Go look at cat pictures or something. So we get this. This is the primary ozonide. It's really explosive. It's got 3 bonds to oxygen. Now we know what we need to do. We need to break this carbon-carbon bond. I'm going to try and explain it differently this time than I've explained it before. We need to break that carbon-carbon bond. We know that needs to break. So let's start by breaking it. And the only way we can do is we can break it into either one, top or bottom, doesn't matter, same diff. If I do that though, and again, let's keep track of lone pairs. that oxygen is now making using 5 orbitals. And that is forbidden. And so we need to break a bond because it's the only thing we can do. Not really. It does not matter if there's methyl on one of the carbons. If a methyl group made one of the carbons cross double bond or substitute with that negative oxygen attack that carbon preferentially over the other. No, it would actually attack the other one. If there was, like, if I'm going to put a substituent on it, I would put it on this one because this is less hindered up here. There's no charge, so there's nothing attracting the negative to one side or the other. But you can't tell because this is a resonance structure of the other thing. It's not like one of these oxygens is actually more negative. They're both the same. It's just I've drawn one of the resonance structures. It doesn't matter what's associated there. Substitution is irrelevant. Okay. But I guess I am drawing. You can, but what I've done is I've attacked this carbon. I've used the double bond to directly attack this oxygen. I'm not drawing an intermediate because there's no real intermediate there. There's no it all happens at once, really. All these arrows happen at once, and I'm arbitrarily drawing one of the arrows first. Somebody asked me to add a methyl, so I added a methyl. There's a methyl now. It doesn't matter. It doesn't affect the mechanism. Because it's not. Nope, it only has 2 bonds. There's nothing wrong with that oxygen. That carbon over there is positive. Oh, the first one here is positive because it's got 3 bonds. It's only got 2 electrons. This one over here was me screwing up. Well, they do, but there's already a lone pair on this oxygen. So this oxygen's already using 5 bonds. So let's just take a look at ozone for a second. Really good question. Why don't the positive and negative want to join up? So let's do that. Now we got a problem. That's neutral. For sure. But that oxygen is using 5 orbitals. Impossible. Or rather, I've been reading the Princess Bride again, so it's inconceivable, like completely inconceivable, and I do know what that word means, and it is inconceivable for that oxygen to have 5 orbitals involved. And if you haven't seen The Princess Bride, you really have to go watch The Princess Bride. It's probably a better use of your time than a study. Okay, so now what we're going to do is we've got this kind of nucleophile electrophile system over here again. Obviously, if I take a look at what this oxygen wants to do, little sidebar, we could draw a resonance structure. You'd be a moron if you drew the other. Next time I teach this course, I'm going to teach it entirely using Princess Bride memes. And you'd be a moron if you didn't try and draw this way. Positive charge on the carbon, negative on the oxygen. Now these arrows are hard to follow. right? I I find this a little bit tricky. And so again, what might be useful is if you need to, please, please, please number your atoms. Go, okay, atom A needs to be attached to atom B, and so forth. But what we know is that I'm just going to draw it like that. This oxygen here, you know what? I got multicolored pens. We kind of have a thing like this. So we have this 5-membered ring. It's a little weird because part of it's kind of sticking in instead of sticking out, but it's a 5-membered ring, 2 oxygens, carbon, oxygen, carbon, back to the 2 oxygens again. And this is always what these secondary ozonides have. They have 3 oxygens in them and 2 carbons. That's still pretty unstable. I can't do anything else with it though until I add the triphenylphosphine. I like the purple more than any other color. I'm going to use that as a nucleophile, and it's going to attack one of the oxygens. Either one, doesn't matter which of these two, does not matter at all. That forces this oxygen to break a bond. It's going to break the oxygen-oxygen bond because that's a weak-ass bond anyways. That's going to generate an oxygen-carbon double bond. That's good. But then that carbon would be making too many bonds. So we need to break one of the bonds to that. Well, let's break this carbon-oxygen bond. And it can come in and make a carbon-oxygen double bond, which is great. But then this carbon will be making 5 bonds, which can't happen. So we'll break a bond to oxygen. And we follow all of those arrows. We get that. Well, yes, this is a 7-membered ring. So it's got the 6 original carbons that were in this ring, plus an oxygen. Yes, dimethyl sulfide could equally have been used in place of triphenylphosphine. It's exact same thing. There are lots of other things you can use too. Those are the 2 I'm introducing because they're the most common ones that we actually use when we're actually doing this in the lab. And you're done. That's it. That's your ozone. That's your ozone dialdehyde. So what you've done is you've chopped the double bond and produced 2 aldehydes or 2 carbonyls. Okay. Okay, so before I get to that, I want to make sure we touch on something. So let's say you had this molecule. Let's do a few different examples with it. Okay, so example number 1. Ethanol and heat. Okay. So I've told you that we're not going to do... Yeah, I can go back for a second. You ever have a headache and you're not quite sure if it's because you haven't had enough caffeine or it's because you've had too much caffeine? And so you decide that the only way forward is to have more caffeine? Yeah, that's currently where I'm at. I have no idea how many. Yeah, I will. You know what? I'll actually do that in this example here. No, I'll make another example for a Grignard. But we've got time. So we have. I actually have caffeine pills, and we do some stuff with caffeine. So when you're looking at this, you should be thinking, okay, am I under strong basic conditions? Do I have a strong reactive material in here? And the answer is clearly no, I don't. I've got neutral ethanol. I've got neutral styrene material. Um, don't have a really strong preference for E2 or SN2. Now, for E1 or SN1, I'm thinking, do I have a really good carbocation? Is it resonance stabilized? No, there's nothing around there. Is it tertiary? No. Okay, so we don't have a really, really strong nucleophile or base. We don't have a really strong carbocation. So we're kind of not really favoring any of them. But there's heat. There's a lot of ethanol. Something's going to happen. So this is the problem with secondary carbons. I think under these conditions, with the heat and the ethanol is so not all that reactive that you are going to generate the carbocation. We are going to make the secondary carbocation. And this is then going to react. Now, is it going to be doing an elimination or a substitution? I would accept both. Now, an argument for an elimination is you're going to need a lot of heat to make this go, and heat favors the elimination. The argument for the substitution is it's a secondary carbocation, so it's quite accessible. So you could actually, I could give you a question basically saying, lay out your argument for why this is going to be one or the other, and lay out the argument against. So it's kind of like you argue both cases. Why an elimination, why a substitution? So why an elimination? Well, I can make a pretty good double bond. That's a good double bond. It's tri-substituted. Janik, that's literally it. I actually kind of need to get somebody at some point to make a little video of this kind of thing. So heat is E1 favoring, but secondary and stick is SN1 favoring. Right? So we have things that favor both. I think if you held a gun to my head and said, what's the major product? I'm going to say you're going to get an elimination as your major product. Sorry, not a substitution. Because the stick and a more accessible door, like we have a smaller cat and we've got a nice big door because it's secondary. Now, if we take exactly the same molecule, we treat it with I minus. Okay, now suddenly we've changed the calculations because we're adding a much better nucleophile. It's now more reactive because it's negative. Let's say we play around with it and we add some DMSO as solvent. And now we know it's a polar aprotic solvent. So suddenly the carbocation is not looking as favorable. And it's not so much that anything's changed about how easy it is to make the carbocation. The carbocation is about the same. A little bit harder to make because we now have an aprotic solvent instead of protic. Ethanol is a protic solvent. But the big thing is we have something that can happen faster than carbocation formation now. Suddenly we have an alternative. And the alternative is using I. And then what you need to know is, okay, so is that likely to act as a base or a nucleophile? If it acts as a base, we're going to make HI, hydrogen iodide. Hydrogen iodide is a really strong acid. That's not a really easy thing to do. And so iodine, like cyanide and azide, was on our list of things that normally act as nucleophiles, not as bases. So I expect that to come in, and I expect that to do an SN2. Polar product is favored by things that make carbocations. Polar aprotic is favored by things that do not make carbocations. Exactly. Cool. Okay. Yeah, but this one's not tertiary. If that was tertiary, if it was tertiary, let's just move it over. And I use something like sodium iodide in DMSO. Solvent's not normally the most important factor. It normally is sort of like win more. You do better on something, but it doesn't normally tilt the balance. It gives you some clues on what you should be looking for. But if we move that over, iodine's still a really shitty base. You're just not going to make HI. So now, although this is still basic, theoretically, same conditions as in SN2, now you have a tertiary leaving group. And so what I expect it to do is I expect it to generate a carbocation. And it's a shitty base. And so I expect it to do an SN1. It's not so much that I expect it to as it absolutely will. There is no way it's going to do anything else. But these secondaries are really iffy. The bottom one, happen equilibrium? Yeah, it does. It probably depends how much sodium iodide you got. If you got a lot of sodium iodide in there, you'll drive it forward by Le Chatelier's principle. Yeah, it would be completely appropriate for me to ask you, do you make an E or a Z? You almost always, whenever you have an option, you would have a complete option to do either one here, you would always make the E enolate. Yeah, E is more stable. Well, you make the E enolate with respect to size. It might not actually be an E enolate. You can get a Z enolate, but you'll put the two biggest groups trans to each other. Yeah, so the antiperiplanar comes in for the elimination. So let's do an example of that. No. Yes. No. No, I'm sure I've thrown this into one of the assignments. So let's say we have this molecule here. And we treat this with isopropoxide and isopropanol. I'm not 100%. So Ying asks, how do you know the second purple structure was the major product, not the one with the double bond? So why the substitution over the elimination? I'm not 100% sure. But I've got a smallish stick-like nucleophile, which favors substitution. I have a very open available secondary carbocation. So there's not a lot of steric bulk that's preventing substitution. So substitution seems kind of likely. But the elimination is possible. Bennett, I skipped your question. Is E1 product for this insignificant for the bottom one? Yeah, it is. Iodide is a crappy base. The E1 product is insignificant. So in this example, we've got two spots and a placeholder. And so we know, hopefully you're looking at this and going, okay, ball, basic, E2. I'll come back to that Kyra in a second. So hopefully you're thinking ball, basic, E2. Great. You've got two options of hydrogens to eliminate. But you don't really, because this hydrogen here is not anti-periplanar to that bromine, whereas this one is. So you don't really have an option. You are going to eliminate that hydrogen because you need to be anti-periplanar. And so your product from this reaction is going to be that. So Kyra asked if SN1 happens faster than E1. It depends on the situation. In this top case here, if this is the major product, then yes, the SN1 happened faster than the E1. This is a Zaitsev base. You need the extra methyl group to make it into a Hoffman base. Only the most bulky ones are Hoffman bases. Everything else wants to do is Zaitsev. Okay. Grignard time. Yeah, I was going to do an LCAO, but I think we've covered enough of those. I don't have time, so I'll probably do one in office hours at some point. If you can do all the assignments and questions in the assignments here, I'm probably okay for the final. And yeah, anti-periplanar is only for E2. Yeah, it's not relevant for E1 because you have a flat carbocation, so you can eliminate anything. Yeah. Mm-hmm. Why is it not Hoffman? Because it's not a Hoffman base. It's not big enough. There's also no proton. There is no Hoffman product possible. You need normally a really big base to a Hoffman. Yeah. So this one's out of the page, so it's not anti-periplanar to this bromine. It's not lined up with that. So you need to go back on that. You need to go back to the maybe go back to the lecture where we talked about E2s. If both were out of the page, like both methyl groups, like if both hydrogens were into the page, you wouldn't get any selectivity. It could be one or the other. It does. You just don't have as free rotation in manual. So Emmanuel asked, I remember an example we had drawn Newman protection to decide if it was E or Z. That doesn't apply to rings. It does. It's just you can't rotate because it's a ring. You can't access everything. It's just tied around. You don't have full freedom to flip everywhere. Yeah. If you did, it wouldn't matter. A positive charge on a primary carbon is so that versus a nitrogen with only 6 electrons. Probably the primary carbon. They both suck. They both don't exist. Nitrogen with 8 electrons is far more stable than a primary carbon carbocation, though. Okay. I'm going to do a quick Grignard example. LCAOs inherently take resonance structures into account because you draw in all the orbitals. And so you have all the orbitals required for all the resonance structures. But yeah, you need to kind of look at what's possible. Like for this one, for an LCAO, you would need to identify that this is sp2 hybridized before you drew the LCAO. I want to quickly get to an example with a Grignard. So a Grignard example. It's good that we're running out of time because my tablet's heating up. You know, this computer's getting old, I guess, and it's starting to heat up too much. Maybe I need to reformat it or something. So this is basically just equivalent, largely, to methyl minus. And so this acts like negative opening of an epoxide, or negative opening of a bromonium, or negative opening of anything. It acts like a methyl minus nucleophile. And so if this is looking at an epoxide like this, we know that although this is the site that we attack if the thing is positively charged, this is the more accessible carbon. So if there's no charge on this, none, there isn't any on this epoxide, then we expect the methyl group to attack this carbon. And so we ring open the epoxide with a methyl. And this, again, if you need a reminder, is called a Grignard agent. And we're at 223, and I think that's where we're going to stop. No, I wouldn't prefer the tertiary because although the tertiary it's more hindered. The plus would prefer tertiary, but it's not positively charged. Grignard is on the final, but no other carbonyl stuff. Because Grignards can be used for epoxides and other stuff. No, manganese tetra. KMNO4 is part of the alkene chemistry. I'm not sure there's a lot more to be done here. So you would just add water. It will probably be this. 2 would be water and acid. And we're just going to protonate. And so we've added a carbon to this thing. Yeah, manganese MnO4 is the same as osmium tetroxide. I don't think I covered. It could. You will have MgBr plus. You could draw a bond there, and then it would then hydrolyze and give us OH. It's completely proper to do that. Fatima, it's not necessary, but it's completely appropriate as well. Lara's asked half a question. Because it's a negative, it's a nucleophile. And nucleophiles want the easiest to hit place. And the easiest to hit spot on that is the last substitute carbon. Yes. I thought I've said that a bunch of different ways, but I obviously haven't said it enough ways. So yeah, when you're opening an epoxide under basic conditions, you attack the most accessible carbon. When you're attacking under, and that makes sense. That just makes sense. Always attack the most accessible thing. It's just when you're opening under acidic conditions, you have that partial positive charge now. I'll draw a separate one. Now, for obvious reasons, you can't do this with the Grignard because it would just react with this hydrogen. But in this case here, now you got the delta plus here and a little one here. So this is now basically sending out a siren call for any nucleophile present to attack here because it's positive. But it's only delta plus because this is positive. If this isn't positive, it's not delta plus. Well, it's still a little bit because of the oxygen carbon bond polarization, but very, very minor. It doesn't matter. Yeah. You know what? I don't think anyone enjoyed this semester. No, methyl minus attacks the least substitute. Here it would not work because if you had methyl minus in here, it would attack the proton. It wouldn't do anything with these. It would ignore the carbons. It would just go after attack the proton and make methanol or methane. But yeah, no, I thanks everyone for having the semester. I know this isn't what any of us wanted. It's pretty miserable. Um, yeah, I think we have another semester of this, but then hopefully the fall we're back in person. Good luck. Um, I hope I don't ever see any of you in this class ever again when I teach it again. 9 a.m. to 10 a.m. tomorrow and Friday. Okay, take it easy. Thank you guys for being a good class. This was the best it could have been under the circumstances. Oh, my power just died. That was interesting. My power just died, but I think this is probably dead.